Good morning. It's just afternoon, actually, by literally 1 minute. Good afternoon, here, 13s. Transition metals, aqueous chemistry, lesson 5. Is it 5 or 4? I don't know what it is. So guys, we're going to be doing Cobalt today, but before I do that, I'm going to, first of all, start off by going through the Chromium exercise. You guys have just been given 15 minutes. It was a 15-mark exercise on Chromium, and I'm going to go through these marks straight away. So I'm going to share my screen. Share my screen. Hey, Winkit, good to see you, man. Good to see you, dude. Right. Okay, I'm going to hide that. Right, what I'm now going to do is I'm now going to stop my camera there. Now I'm going to attempt to disable my camera. If it crashes, I'm so sorry. It's already crashed once on me today. Cool, survived. Okay, right. So the Chromium exercise. It was just nice to apply what we're learning in these transition metals into exam-based questions. So they've given you this rather disgusting kind of series of reactions all linked together, and they're asking you to be able to use your understanding and knowledge of chromium complexes and chromium aqueous chemistry to be able to identify and give observations and whatnot for all of them. So, okay. So the first question, it says, identify the gray-green precipitate A. Okay, so they've taken chromium 3 hexaaqua, the hexaaqua chromium 3 complex, and they've reacted it with sodium carbonate. Now we know straight off the bat that it's a +3 ion, and I do love transition metals. Once you get the rules, you've got the rules. So the precipitate is going to be because 3 pluses don't form the carbonate. They're too acidic for that. What they're going to do is they're going to form the triaqua it's going to form the triaqua trihydroxy complex, yeah, which is neutral, which is why it's a precipitate. And that's because the 3 plus have got a pH of 3, which is acidic enough to destroy the carbonate ion. The 2 plus is a pH 5, and they just bind to the carbonate, forming the carbonate. Gas B, of course, is carbon dioxide. So we're going to see effervescence. It's only slight. The practical is actually really good to do because it's so difficult to see it. You get these tiny little bubbles. What's the equation? Right, much more challenging equation here now, folks, because we've now got the chromium hexaaqua 3 plus is reacting with the carbonate ions. Now, the sodium doesn't need to be used. Just to let you know, you can just disregard the sodium. And what we're going to form is we're going to form CO2, we're going to form water, and we're going to form the chromium triaqua trihydroxy complex. And yes, it's tricky trying to do this all on one line. Totally understand that. And that complex, of course, is no charge, so it's a precipitate green. They call it gray-green. Now we need to balance that equation. It's easier just to learn this, which is 3, 3, 3 in the middle. I always like that one. I think that's right. There are 3 carbons, and then the hydrogens you see. So this is lost, that there has lost 3 hydrogens. So we need 6 of them for the water, so we've got to double that as well. So it's something that it's worthwhile just learning rather than trying to, because if you build that, you'll probably make the mistake in the exam. You'll either balance it incorrectly or whatnot. So it's definitely something that's worth practicing. Notice that I put the 3s in the middle. Yeah, and the 2s on either side. So just showing you tips to be able to how to handle that one. Okay, identify reagent for reaction 2. So reaction 2, we're going from the triaqua trihydroxy complex, and we're forming the hexahydroxy chromium 3 complex. So what that means is we're going to be using concentrated or brackets excess sodium hydroxide. There we go. So in order to get a full swap out, we're always going to be using concentrated NaOH, which of course concentrated means it will always be a massive excess. I would emphasize the word concentrated. If it's asking for the reagent, it's definitely worthwhile saying it. Next, deduce the oxidation state of chromium this is the yellow chromate ion, and it's a +6. Let's have a look at that. Let's dismantle it. So CrO42 minus. I've got oxide ions, but I've got 4 of them, so -8. The overall charge is -2, so for me to get from there to there, the chromium must be bringing a +6. I like it. Okay, so +6 for the chromium. The next one, identify the agent for reaction 3. Write a half equation for the conversion. Right, what's the equation for reaction 3? We're oxidizing it. We're taking it from chromium 3 plus up to chromium 6 plus. So we need an oxidizing agent. There's only one oxidizing agent that we use for transition metals, and the reagent is hydrogen peroxide. So the half equation, which is interesting, that's, again, more challenging. Cr brackets OH6 3 minus going to, we need to moe this, CrO4 2 minus. Right, we're going to moe it. Now, the annoying thing is, though, we're in alkali. So we've got to do moe and then convert. This is a bit of a nightmare. So what I'm going to do is I'm going to use the space at the bottom to do my process. And anyone who's forgotten how to do this process, this is great revision. So let's moe it first. So moe stands for 3 minus going to CrO4 2 minus. So the first thing, the M stands for metal. 1 chromium, 1 chromium. We're good. Water is for oxygen. So I've got 6 oxygens here, but only 4 oxygens there. So I need 2 H2Os on that side. Right, now I've done the oxygens with water. Now I can do the acid. Yeah, and acid, of course, is H plus for hydrogens. So on this side, I've got 6. Yeah, but on this side, I've only got 4. So I'm going to have to add H pluses to this side. I'm going to add 2 of them. Right, I've done my acid. Now I need to balance for electrons. Yeah, so now I'm up to the electrons. So let's check the charge. So I've got -3 on this side. On this side, though, what a mess that is. Don't forget my conversion. On this side is a mess because I've got -2 from that guy, but then +2 from that guy. That gives me an overall charge of 0. What that means is I'm going to have to add 3 electrons onto this side because I need to bring it down, remember. That now gives me -3, which is the same on either side. So I've now balanced for electrons, but now I've got to remember to convert because I'm in acidic conditions. To convert this, I use my lovely dissociation of water equation. So H plus OH minus goes to H2O. Now, the great thing is I need 2 H's, so I just double everybody in the equation since it's a 1-to-1-to-1, and now I put them together. So the H pluses now cancel. What else cancels? Absolutely nothing. Right, so yeah, nothing else cancels. So the final equation that I'm now going to write down on my lines is going to be, let's just divide it in half, everything on this side. So I'm going to use the slightly longer line here. So chromium hexahydroxychromium 3 complex is reacting with 2 OH minuses to give me a chromate ion, which is yellow, plus, waters add up, plus 4 H2Os and 3 electrons, and I'm done. That's hard, folks. That there is A2 chemistry at its best. Yeah, you've got to run a process, which we've got before, then we've got to convert it, and we can even check that to make sure it's all okay. It's great chemistry, that, folks. Really hard. That's a grade A star. So on this side, 1 chromium, 8 hydrogens, 8 hydrogens, 6 oxygens, 8 oxygens, 8 oxygens, and then all adds up, and then charge. Don't forget that. So now I can check my charge. So on this side, I've got +3, -2, total charges +1. Then I've got -2, and then, there's a problem. Oh no. It doesn't add up. Oh dear. What have I done? I've made a mistake. Oh, you see, guys, that's why you check it. I've made a mistake. So let's go back and have a look at my halves. Right, what have I done? +3. Right, let's go back to here. Let's just check it. My conversion was correct still. Yes, my conversion was right. It's my electrons that are wrong. So let's just get rid of it down to here. So on this side, I've got +3. But on this side, I had -2 and +2, which was 0. I had to, that's why I wrote it down as mine. Oh, hang on a minute. It was minus. I apologize. Guys, I am correct. So easily done. It's all correct now. I'd written down the wrong charge. I'd written it as a 3+ instead of a 3-, and now all adds up. Perfect. Whew. Glad I caught it. Fun. Next. Draw the structure of the chromium-containing species in reaction 5. Indicate the charge on the species. Reaction 5. Okay, so this is the chromium 1, 1, 1, 1, 1, 1. I'm going to make that into a wedge, line, 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 line. And then I'm going to go N, 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 and N, and then carbons, and then carbons, and then carbons, and then line, 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 line. Takes practice. There we go. Put it all in. All those are H's, square brackets, and that's going to be +3 because ethyl-diamine is a neutral ligand, so it's going to be +3. Isn't that nice? Wow, that was tough. Okay, so 3-dimensionally as well. It's awesome. So indicate the charge. Perfect. Okay, explain by reference to charges. To changes in bonding why the enthalpy change for reaction 5 is almost 0. The reason being is we went from this complex where we had ammonia bound. This was just NH3. NH3. We're breaking and making the same bond because the bond we're breaking is we're breaking the chromium-nitrogen bond. Yeah? So that bond, that bond, that bond, that bond, that bond, and that bond we're breaking, and we're making exact. So we're actually, sorry, we're breaking these are breaking, and these ones are being made. And they're exactly the same. So same bonds being broken as made. So delta H close to 0. By the way, second question that usually goes on this, why isn't it 0? Because we're using mean bond enthalpies, because bonds that are the same will have different strengths depending on the compound they're in. Another very common question. Next, identify the chromium. By the way, just to give you some marks, by the way, that original diagram, I'm going to get rid of all this now. Yeah, that diagram there is 2 marks. That's 2 marks. Same bonds being made as broken. Next, I believe that's correct. Yeah, and then marks 1, 2, 3, and the correct equation. That's hard, that for 1 mark. 3 marks, 1, 2, 3. Yeah, this is all adding up okay. Next. Okay, identify the chromium-containing species present in the blue solution. Formed in reaction 6, the role of zinc. Reaction 6. Ah, there it is. So reaction 6 is forming the chromium 2+ hexaaqua. Chromium 2 is blue. Yeah, hexaaqua, chromium 2+. And that is a blue solution because it's charged, and the zinc is a reducing agent. Nice one. I like it. No equations. Yay. Next, identify the organic product with a low boiling point. Identify the main organic point when it's refluxed. Okay, what's going on? So reaction number 7. Okay, so reaction number 7 is, it's clear what that's happening. They're using potassium dichromate, which is orange, and they're oxidizing ethanol. Now, that's really clever. We know that there's a 2-step oxidation. Oxidation 1 followed by oxidation number 2. Oxidation 2. This one's done under distillation, and we form the aldehyde. Aldehyde. So the organic with the low boiling point is ethanol. Yeah, because it's dipole-dipole attractions only, no hydrogen bonding. And the main organic product when refluxed is ethanoic acid. I like it. It brings us to the end of the sheet. 15 marks. Boom! Love it. I'm loving it. 15 marks. I like it. Guys, how did you get on? Add your scores to the sheet, please. That would be grand. Cool. Add your scores to the sheet. Right, so today's lesson, I've got 20 minutes. Let's see how fast I can do Cobalt. Ha! Today's lesson is Cobalt chemistry. So we've got 2 things, Cobalt table colors. So sodium hydroxide little, sodium hydroxide excess, ammonia little, ammonia excess, and sodium carbonate, and then Cobalt oddities. And there aren't that many actually for Cobalt, which is quite nice. Only 1, I believe. Cool. So Cobalt. Woo. Okay. So Cobalt. First of all, we're going to start off with, let's say something like calcium. Cobalt dichloride solid. So if this is anhydrous, it's nice to remind ourselves of this. If we have an anhydrous transition metal compound, then it is going to be white. We know this, it's just a white solid. And then, of course, we add it to water. So first one, we're going to add to H2O, add to water, and the first thing I'm going to form is I'm going to have cobalt form a complex, and it's going to be the hexa-aqua cobalt 2 complex. And that is pink. Gotta love cobalt. And by the way, it is also aqueous because it has a charge. Yeah, we know if a complex has a charge, it's aqueous. So we form the cobalt hexa-aqua 2+, and it is pink. Cool. So the next one, we have cobalt, and we're now going to add sodium hydroxide, but we're going to add a little of it. Remember, the littles are always the same. Gotta love the rules. I love the rules. So cobalt, we're going to form the tetra-aqua dihydroxy complex, and it has no charge, so it's a solid. So the question is, how do I always remember that? The reason being is, in the equation, whenever you have a transition metal hexa-aqua ion, whatever the charge is, the number in the charge is going to tell you the number of OH minuses that will react with it in the first place. Yeah, this is always the littles. Yeah, and when it's gonna act as a base in this case, a Bronsted-Lowry base. It's gonna remove 2 protons, and I'm going to form transition metal with the tetra-aqua dihydroxy complex and 2 waters, and it forms a precipitate, forms a solid. Now in this case is pink blue. So we've now just formed, it's actually quite a pale blue in reality. Yeah, I'm trying to think of the kind of blue it is. It's kind of that kind of a blue. It's a bit paler than that, I think. So pink, blue. Now the next thing. Okay, so the next one is we're going to add OH minus, but we're going to add excess. So in this case, we're using the reagent is concentrated sodium hydroxide, and we get, now the 2 pluses aren't acidic enough. However, so what's going to happen is I'm going to form exactly the same thing that I did before. So I formed that. The reason being is because it's not quite acidic enough. It's not going to lose any more. So I'm going to form the same blue precipitate that I did originally, but there is another observation. Now, because we have now got the OH minus in excess, yeah, it's now in alkali conditions. Now, since it's now in alkali, this is why I switched to purple, because this is now in alkali conditions, it can now go through oxidation. This is on standing in air. On standing in air. I think people might be asking questions. Charge on the, should be 3 minus. Oh, thanks, Julian. Julian picked up on my mistake earlier. That's amazing. Love it. So it now is going to go through an oxidation process, and it changes color. It actually turns into a fleshy brown color. This is cobalt tri-aqua trihydroxy, and it is also a precipitate because it has no charge. Because what's actually happened, as I said, can I just point out, in your exam, it turns like a fleshy brown color. And all you actually need to state in your exam is that it darkens. I quite like that. That's kind of a workaround with this stupid color. Yeah, that's an exam answer. Yeah, you can just say darkens on standing. Yeah, but in reality, it's a full change. Turns into like a pale pink, pinkish, fleshy color. But it is also as precipitate. It will also happen at the surface. If you're imagining this happening in a test tube, yeah, once the OH minus is in excess, we form that gelatinous blue gunk, yeah, but then what it starts to do is it starts to brown at the surface where it's coming into contact with air. Yeah, and by the way, you do actually tend to see a little bit of the greeny color as well when you're seeing the brown mixing with the blue. That does happen. Check it out. I just want to show you that now because it's awesome. Dixon's the only one who hasn't pulled in his score yet. Okay, so just to show you this, cobalt excess sodium hydroxide, NaOH. Google doesn't tend to like me doing that, but let's have a look. I'd love to see a real picture. This is where we'd be doing it in class if we were in school, and it's really annoying. Oh, check it out. Look at that. So can I find something better? And you can see it's on standing. So it forms the blue-green, the blue precipitate, and then you can see the kind of the greeny color starting to appear as they mix together. It's kind of nice. The chemistry here is really, really good. Let's go back to my notes. Okay, so it darkens on standing. Let's now go to the next one. So the next one is going to be ammonia little. Yeah, now the great thing is the littles are the same. Yeah, but the equation's not. I form the same precipitate, the cobalt tetra aqua dihydroxy complex, and it is the precipitate still, which is a solid, and it's blue again, a blue precipitate. And but in reality, the equation, just to show you that the equation cobalt hexa aqua, everything starts off at hexa aqua. It's a 2+, yeah, and then reacted with 2 amines. Remember, the 2 is always match. Yeah, and I then form 2 ammonium ions, yeah, plus the cobalt tetraaqua dihydroxy complex, which is electrically neutral. Yeah, sorry, my laptop's struggling a bit. I've got a bubble underneath the screen. But anyway, so it's nice to see how the equation differs, but the product, the precipitate, is still the same. Right, now what happens when we now do this with excess? And this is kind of special. This is ammonia excess, and this is kind of special for cobalt. Cobalt goes through complete substitution, a bit like chromium does. Chromium does a complete substitution as well. So we get cobalt hexaamine with a double M, hexaamine cobalt 2+ complex. Yeah, and that is a solution now, and it goes pink, blue, straw yellow. And I know, guys, it's a nightmare that you have to remember the number, but it turns into a straw yellow solution. Complete swap out. Now, here's the next problem is now, of course, I've zoomed in. I'm too close to the edge, so I can't do my oxidation process, because just like, move that down to here. So just like the cobalt in excess sodium hydroxide, this also goes through an oxidation process on standing. Now, of course, again, it only does it in excess, because the little is not in alkali conditions. And what this now forms is the cobalt, it's the hexaamine cobalt 3+ complex. It oxidizes and it darkens. This one does actually darken. Yeah, it goes from a straw yellow to quite literally like an orangey color. It goes to like that maybe. No, it's darker than that. It's darker than that. It's about that. It goes to quite a dark color. So it darkens, and you can actually just quote, it darkens on standing. You still need to know the equations for it, and you need to be able to build them, but it's like, it's reasonable in terms of observations. The last one is the carbonate ion, and the great thing is about cobalt is it's a +2. So all that's going to happen is I am going to form cobalt 2 carbonate. Yeah, and just to tell you, it is indeed a solid precipitate, and once again, it is pink. And I do love that. It returns back to its original pink precipitate. Cobalt carbonate, pink, blue, straw yellow, pink, and remembering the 2 darkens in excess, alkali being the oxidation processes on standing. Now, that is cobalt in all of its beautiful glory. So the next thing is I just want to do cobalt oddities. So cobalt oddities, and you don't really have many. Yeah, oddities. The only cobalt oddity that I know that you must know is cobalt chloride. So we know that copper does a chloride as well. Just a reminder, copper does CuCl4 2-, and that is a beautiful yellow color, but when mixed with water, you also tend to see it as green. Now, cobalt has a color as well. So cobalt tetrachloride is blue. Cobalt tetrachloride 2- is a blue solution, which is rather lovely. And of course, this is formed when aqueous cobalt is reacted with concentrated with conch HCl. So let's just look at that. It's nice to obviously go back and have a look at some images. So if I just go cobalt concentrated HCl, you see it's actually oh yeah, that's copper. Irritating. There we go. And it is actually a really beautiful blue. It's like it's kind of like it's not dark enough to be. It's not the ink blue of cobalt of copper when it's got the tetraamine diaqua complex. But in this case, it's a beautiful blue, crystal clear as well. Really, really lovely. It's one of my favorite colors is the cobalt chloride complex. And that's all the oddities that you need to know. So loads of blues for cobalt. They do like it. I will post the homework since I've already made it. I will post the I will post the homework sheet for you guys to have a go at. But also, guys, I'm going to send you the link to the YouTube video of the cobalt chemistry so you can watch it. Guys, I'm going to leave you be at that stage. We've done a really nice lesson there. Been nice and quick. I'm really happy with it. So let's turn the camera back on. Enable device. And then I can go back to my StreamYard and I can start my camera and bring you guys back. Right, guys, I hope you found it. I hope you found it okay. I hope you found it useful. If you've got any questions, please feel free to send me a message on Google Hangout. Guys, have a nice rest of your day, and I'll see you soon. See you all soon.